So you can have a look at the recorded tutorial, and if you have any questions on the recorded tutorial, we will be arranging a question and answer session where you can ask questions about the tutorial. Okay, so for tutorial number 3, please look at the recorded tutorial on Adventure. So this morning I want to look at tutorial 4. So the first question on tutorial 4 is also about data dependencies. So we're given a code fragment. We load data from address R2 into R1. We have an addition of an immediate value 1. We write the data back from R1 to address R2. Then we have another immediate addition of 4 to R2. Then we subtract R2 from R3 and put the result in R4. And then we have a branch instruction which takes the value of R4, and if R4 is not equal to 0, then it will branch back to the beginning of the code segment.
Then got another one, the UI one, right? Right, I was looking for that. I think the I means what? Immediate value. No, wrong, right? There's one.
Okay,
Is
so
it below also?
first of all,
Immediate value.
we're asked to list the data dependencies in this code. So can anybody tell me what data dependencies we have? There are different sorts of dependencies. The true data dependency is read after write, but we can also have write after read and write after write dependencies. So can somebody point out some dependencies here? What about register R1? What sort of dependency is that between instruction 1 and instruction 2?
Read after write.
Is it? Read after write. And you also have a write after write dependency as well, because instruction 2 both reads R1 and writes R1. So there's a read after write and a write after write. Any other dependencies involving R1? What about R1 here? Again, we're using the value of R1 here to store it into memory. So we're reading the value of R1, so it's a read after write. R2?
Read after write.
Oh, so yeah.
You read then you write.
You're right.
I'm right. Read after read.
You're getting the best.
I think the R2 is.
Okay, so here we're using the value of R2. So we're reading the value of R2 and we write it in the next instruction. So that's actually a write after read dependency or an anti-dependency. And similarly, we can also consider this a write after read dependency, because here we read the value of R2 and then write it here. In a simple pipeline, that shouldn't cause any problems, but it is an example of a dependency. And then for R2, we have a true dependency. Here, we write the value of R2, we read it,
Read after.
and we also have a true dependency for R4. Here, we write the value of R4, and then read it.
Right after right.
Right after right. Why he say
Right
right?
after right.
When he say right, then read. I think he also go.
See his small
Yeah.
Okay, so the list of the dependencies are follows. True dependency is read after write. Output dependency, write after write. Anti-dependency, write after read.
He go and skip.
Mm.
Can you pass that around, please?
What is I?
Okay,
Instruction.
is everybody happy with that? Any questions? Okay. So, what we're asked to do now
Got so far. Got 7.
No lah.
Correct. Got 7.
Yeah, correct.
we're told that we have an architecture with a 5-stage MIPS pipeline, which I think you've covered in the lectures. In this case, we're told to assume that we have no data forwarding except forwarding through the register file. Okay, there are different types of data forwarding. Data forwarding through the register file is when you can write to the register in the first half of the clock cycle and read from the same register in the second half of the clock cycle. Okay, so that's data forwarding through the register file. In the next part of the question, we'll consider full data forwarding, but for the moment, we're just going to have data forwarding through the register file. We're also told that the branch is resolved in the execution stage of the pipeline. And the program counter, if we take the branch, the program counter is updated in the mem stage, the M stage. Okay, so when we resolve the branch, then there may be some delay because we have to wait for the program counter to be updated before we can get the correct instruction. Okay. So first of all, we're asked to fill in this table, and then we're asked to calculate in total how many cycles it will take to execute this fragment of code. So this fragment of code will loop. We can work out how many times it will loop, how many iterations there are, and we can work out how many cycles we require per iteration, so therefore we can work out the total number of cycles. So, has anybody done this? Can anybody tell me, first of all, how many iterations per cycle, or so how many cycles per iteration, and then how many cycles in all? Has anybody done this?
This whole thing takes how many cycles? One instruction.
No?
One cycle instruction.
Okay, so let's do it. Let's fill in the table for one iteration, and then we can work out how long it's going to take.
The first one we have to store for one
First stage.
and then divide by then
Sial lah 21. Ayah. Mana lihat sial.
You see,
Okay, so
Haven't finished.
we start off with the first
I put down
instruction.
here. You see, I
The
know that
second
this one is
instruction,
I
remember that
decode
we
this.
have
I
a
thought
true
decode 的时候啊，你可以直接
dependency
做，我为什么要
between
store 了再
instruction
result 出
1
来？
and instruction 2
Yeah, we have
for
dependency.
the
不是
register
不是
R1.
不是是 because 你的
Okay,
你的
so
register 要是拿到才可以 decode 的。
here
我
we
做
write a
错，
value
我
to
这边
R1,
我一 execute
and
可
then
以
we
直
want
接
to read
decode。
that value of R1 in the next instruction. If we have forwarding through the register file, then we can write and read in the same cycle.
You see, like nearly correct right? I go and put a decode in here, it should be store and decode.
Okay, but we still require some stalls because we don't write the value to the register until cycle 5, so we have to stall before we can execute the decode instruction, which will read the value of the register.
Okay, let me say.
So that's the first of the true dependencies for R1. We also have a true dependency between instruction 2 and instruction 3, because here we write the value of R1 and then we need the value of R1 to store the data. So this should be the other way around, shouldn't it? It should be R1 written to address OR2. Okay, so here we write to R1, but then here we need to read R1 to store the value away in the memory address. So again, if we're forwarding to the register file, we can write and read in the same cycle, but again, we still need 2 stalls. We again need 2 stalls before the value is available. We have another dependency between instruction 4 and instruction 5. This writes to R2 and this reads R2.
Wait, help me. This side again.
But in this case, okay, so in this case again,
They all sign, just sign.
we have to have 2 stalls before the data is available. And then lastly, we have another true dependency between instruction 5 and instruction 6 for R4. And again, we need 2 stalls.
I sign.
S is what store?
Yeah, S is in Y.
X execute.
S same
So
Store.
for the read after write dependencies, we lose 8 cycles altogether.
You know why
For
the
this
page
pipeline,
have
it's
to
only the read after write
That's what I do.
dependencies which require the stalls. If you look at the other dependencies, you will see that the other dependencies will not cause any problems. Okay, so the write after write dependency between instruction 1 and instruction 2 is not going to cause any problems, and the anti-dependencies don't cause any problems. It's only the true dependencies. Also, for our branch, we're told that the branch is resolved in the execute stage, but the PC is updated in the M stage. So when we take the branch, we will lose 3 cycles because we can't fetch the next instruction until we've updated the PC counter, the program counter. So we lose 3 cycles due to the branch delay. Okay, so those are the timings for a single iteration. What we need to do now is to work out how many cycles we require altogether. Are there any questions so far before we do that? Okay. So, how many cycles does this loop take to execute?
21 cycle.
Well, you can see that each
It doesn't
iteration
matter. Just
actually
ignore.
takes
You just ignore the instruction.
18 cycles,
21.
but one cycle is overlapped with the next iteration. Okay, so one iteration takes 18 cycles, but because we're overlapping, except for the last iteration, we can count it as 17 cycles. So how many iterations are there?
One cycle is
We're told that initially register
Actually,
R3 is equal to register R2 plus 396. In the code, we add 4 to R2 each iteration, and then we subtract R2 from R3. So each iteration we're effectively reducing, so we subtract R2 from R3 to give you R4. So each iteration we effectively subtract 4 from the initial value. So
Actually, I don't understand the part.
we're told initially R3 is R2 plus 396, and we subtract 4 each iteration, so we can work out that, there should be 396 over 4, which is 99 iterations.
Oh, true.
Okay, so we know there are 99 iterations altogether. So I said that for the iterations except the last one, we can count the number of cycles as 17 because we overlap one cycle. But for the last iteration, we have nothing to overlap with, so we count 18 for the last cycle, the last iteration. Okay, so the total number of cycles to execute that loop will be 98 times 17 plus 18, or 1684.
Eh?
98.
98 meh? Oh, minus 1 cycle ah?
One overlap.
Is it?
Yeah, you see. Wait. Mine is 17.
17 cycle. So what is 98 lah?
Cycle.
17?
98.
Okay, we have 99. The difference between R2 and R3 is initially 396, and we subtract 4 each iteration, so therefore there are 99 iterations altogether. For all except the last iteration, we can overlap one cycle of one iteration with the next iteration, okay? Because we can start to fetch the function
During the execute.
in the same cycle as we write back the register.
That's 17.
So for all except the last iteration, there are 17 cycles for the iteration.
Oh,
So we have 99 iterations altogether, 98 of them take 17 cycles, and the last one takes 18 cycles.
oh, okay, okay.
Oh.
Okay?
But I thought the next one.
R3 equals to
No, because the 90.
18.
Where is this?
No, because got 99 iteration, right? Only 98 iteration will take 17 cycles. Then the last one, right? 17. Because the last one, right, will take the number 18 to do. Then the 17, all the 17 keep looping, right? You only take 17 cycles. Because the W, right? You can. The W thing is that when he add the counter, then he will then do the last branching.
So they take 70 and
Correct.
last one.
For the 99. Then 18 is the last one.
Sorry, how does it overlap? The
5 plus 3.
Okay,
It's because
so
of the execute and the
one iteration takes 18 cycles, but in cycle 18, we are writing back the value for this iteration, and at the same time we're starting the
Also they take
fetch the function,
That is
fetch the
for the
function
last
for
for the last one.
fetch the instruction for the next iteration. Okay, so we're overlapping this cycle between iterations. So really, we only require 17, and then we can start counting this in the next iteration. So all of the iterations except the last one will take 17, but the last iteration takes 18. Okay, anything else?
R3 equals to R2.
396.
360.
Ah, okay.
But I don't understand this part.
Which one?
Because he fetched decode. Never mind. I couldn't see it then.
Okay, so for the next part of this question, we're told
R2
that
plus
we
396.
have full forwarding. So what this means is that as well as being able to forward through the register file, we can also forward from the pipeline stage registers. Okay, so we don't have to wait to write a register. We don't have to wait to write the value to the register and then read from the register. We can forward from one pipeline stage register to another. Okay, so this means that we have more flexibility in the way we can forward the data. So now we're asked to work out again. We start off for one iteration, work out how many cycles for one iteration, and then how many cycles in total. Okay, has anybody done this?
Just now that one is part B only.
Yeah, that one B only.
Yeah, where's the previous?
Okay, so again, it's the read after write dependencies which cause the problem. So here we have a read after write dependency where we write the value of R1, but we want that value of R1 in the next instruction. But now with data forwarding, we can
Do you execute?
forward
Do you execute?
from the pipeline stage registers. So instead of waiting to write the value back to the register R1, once we've completed the M stage, which loads the data into R1, we can forward that data to the execute stage of the next instruction to use that value in the execution of the next instruction. Okay, so in this case, we still need a stall, but we only need one stall because we can forward from the M stage of this instruction to the X stage of the next. If we look at the next data dependency,
Where you get this table?
Okay,
Where you get
here we have another dependency with
The same thing.
R1. So here
This one is for
we
B,
calculate
this
the
one is
value
for
of
C.
R1,
This one
but we
is
need the
only
value of
can
R1
forward
here stored
through
into memory.
register. This one can forward during your your full
this
forwarding
case,
means that during your memory, right, you can you can forward it.
In this case, we don't need to store the value into memory until we execute the M cycle. So we need the value of R1, we need the value of R1 in the M stage of this pipeline here, so we can forward it in the previous stage. However, we still need a stall here because in the previous instruction we have a stall, and this instruction, because we've stalled, this instruction is still in its decode stage, so we can't try to decode this instruction until this instruction has finished decoding. Okay, so we have a stall here, and we forward the value of R1 for the M stage of the instruction. Is that okay?
Store memory, you forward.
Again, we have a read after write dependency. We write, the value of R2 is calculated here and used in the next instruction.
I don't know what's going on.
Here, in fact, we don't need a stall because we can simply forward the data from the execute stage of this instruction to the execute this stage of this instruction. Okay, so this instruction, the execute stage calculates R2, we forward to the execute stage of the next instruction. And here, again, we have a read after write dependency, so we're calculating the value of R4, and the value of R4 is
read after
used
write.
in the branch instruction.
What is
We're
it?
told now
Sorry?
that the
What is it?
um,
Read after right.
the branch
Read after right.
is resolved in the
R4.
instruction decode
R4, why?
stage. So in order to resolve the branch in the instruction decode stage,
This one. This one.
we need the value of R4 for the
Why is it
instruction
after
decode,
Why is it?
so therefore we have to put in a stall here.
Can you say
We
read after
can't
right?
decode the instruction until
Not very sure.
we have the value of R4.
I only know how this thing works.
And then for the branch itself, we predict the branch is not taken. So if we predict the branch is not taken, we will actually get the incorrect instruction. The branch is resolved in the decode stage, and the PC is updated in the decode stage, so we can actually execute the fetch for the correct instruction here. Okay, so in all, with full forwarding, we lose 2 cycles due to the read after write dependencies, and we lose just 1 cycle for the branch delay.
That's it, okay.
So how many cycles do we need altogether? Can you work it out?
Video.
So it's a same thing as just now the answer.
Is it?
Only
How
the
calculate
only the 17.
Okay, so
22,
each iteration,
13.
an iteration actually
20,
requires 12
But then
cycles,
one more is 12. 13.
but
Other one is
3 of the
13.
cycles are
Overlap.
overlapped with the next iteration. Okay, you can see that one iteration takes
So they will
12,
start at
but 3 cycles are overlapped with the next iteration.
9 plus 10 plus 11 plus 6. Oh,
So
9.
for all of the iterations except the last iteration, we can consider the iteration to be take nine cycles because of the overlap. So we have 98 times 9, but then the last iteration will take 12 cycles, so we have 98 times 9 plus 12, which is 894. Okay, any questions?
2 cycle are lost.
Hmm.
How to know if 2 cycle are lost?
Forwarding the second instruction from execute to the next execute.
You want to go from execute to execute? Okay, right. In this instruction here, the value of R1 is stored in memory. So the value of R1 is not actually needed in the X stage. Because the execute stage here will just work out the address in memory where you want to store the instruction, but you don't actually need the value to store until you get to the end stage. So for this type of data forwarding, the general rule is that you only forward when you actually need the value. Okay, so rather than forwarding to X and X, because we don't need the value in the X, you wait a cycle and then forward from M to M. Okay?
And you know what's going on?
Because your store, right? Your store don't even need to execute anything. You just need to get the memory from the
Any
previous
other
one and store.
questions?
That's why you only
Oh, yeah. That's why you forward on for the store.
from the
yeah.
memory to the memory.
If you want to execute,
If let's say you got add anything, right, then you need to answer. Then that's why you from execute, then you bring forward.
okay,
But the
understand.
store you don't even need to execute because the execute only calculate the R2 as it
Okay, so which means for the first one, right? Because your R1 you memory, right? Then for the next instruction you need to execute R1.
Yeah,
right?
because you need to
That's
add the
why-
thing. That's why you put the memory back to the X. The S will execute the calculation automatic.
The F, the D, and the X of the
Then the next one, right, you only need to
For
store
S
store
is what?
R1
S is store.
S is store.
But how you know where you want to put the store? The S.
No, because before you can execute the thing, you need to get R1 right. When you do the add right, but you haven't stored back to your memory, so you need to store a cycle before your previous thing is valid. Then you can calculate, or else your answer is wrong. That's why you need one store.
So 3 over
But you see the instruction 2 and 3, right? You see the store one is after the F, but the second line is after the D.
Correct, huh? Because the third line, right, you need to fetch the thing. Then after that, during the previous one, the add right, you decode. And at the same time, you can one is decoding, one is fetching. It's not doing the same thing. That's why you can continue.
Okay, so I think we move on to the next question.
The order I don't know. The FDS, some got FS, then some got FD.
Because the basic five cycle is fetch, decode, execute, memory, then right. Then in order to have this 5 cycle, right, your only instruction
Okay,
you
so
cannot
again,
overlap the same
question
thing,
number 2, we're
because
given
you only do
a code
one instruction
fragment.
at one time.
So we have 2 branch
So you
instructions
cannot
here.
like fetch one instruction, then you do the instruction, you do at the same cycle of fetching. Then you will fetch
Take the
wrong
value
data.
of R1 and branch if R1 is not equal to 0 to L1. If we don't branch, we add the value 1. Okay.
Value as you add value 1, then the so and so R1.
Why you write like that?
Because the people write that.
Yeah. No, this one is
Add what?
add value R1
Add R0 and
plus 1.
plus 1 to
Ah,
then store inside to R1. Correct or cannot?
Correct lah. More.
Can can also.
Okay, if we don't branch, we add the value of 1 to our 0 and put it in our 1. Here we add -1 or subtract 1 from R1 to put it in R3, and then we have a branch not equal to 0 for R3, which will take us to L2. Okay, so we're told to assume that the value of R0 is 0, so this instruction here will effectively set R1 to be equal to the value 1. Okay, and we're also told that we have a sequence of D values 0, 1, 2, 3, 0, 1, 2, 1. So the first instruction will branch when D is not equal to 0.
B1.
If D is equal to 0, we put 1 into D, and then we subtract 1. So now we have the value 0, and if D has the value 1, we will also subtract 1 and have the value 0. So the second branch will branch in the case that D is 0, in the case of D is 0 or D is equal to 1.
So this one is the value inside. So this one is the pointer. So when you branch, right, it
So
will depend on
what we're
which
told
branch you
to
will go
do
to.
is to draw a table
这个像
showing
this one is like
the
then got a
branch
pointer.
prediction.
Then if let's say your branch equal to 0, right, then your this value will increase or what?
Okay,
so
so in this part we're told to assume that we have two 1-bit predictors. So for a 1-bit predictor, we simply remember whether we took the branch last time or not, and then use that as a prediction for the next branch. So we have one predictor for B1, one predictor for B2, and we're asked to fill in the status, fill in the table, showing the prediction, the action, and the status, and then calculate the prediction accuracy. Has anybody done this? Can you tell me what the prediction accuracy is?
90%. What? You know, in our computer nowadays, the prediction is 98%.
Predict what?
That means the branch.
Is it?
We predict
Okay, so
I think you also very
it's
sure
98%.
Oh.
initially the value of B1 and B2 is 0, so we predict not taken. So when D has the value 0, we predict not taken, and the action is not taken, and the status remains 0. When D has the value 1, we still have 0 for the status, so we predict not taken, but now for the first branch it's actually taken, and therefore we put the status of 1. For the second branch, in the first case we predict not taken, the action is not taken, so the status remains 0. And for the second branch, for D equal to 1, we predict not taken, it is not taken, so the status remains 0. And then I think I'm not going to go through all of the table. I think you can try and work it out for yourself. Okay, if it's taken, you record the status 1. If it's not taken, you record the status 0, and you use the status to predict for the
How you know
next
taken or not
branch.
taken?
Huh?
How you know taken or not taken?
Okay, let's do the first one. Because
So what is the prediction accuracy?
R1 is
Well,
0.
we can count here the number of times the prediction got it right. So here, not taken is correct, 1.
R1
Here got it wrong, here right, 2 times, right, 3 times,
So
this
R1
one
is
wrong,
zero.
this one wrong, this one right, 4,
Branch
5,
not equals to 0. So
this
You
one
won't
right,
branch,
this
never
one
branch.
right, 6 and 7, wrong, this one right, 8,
so the first one is
this
not
one
taken.
wrong, this one right, 9.
It is just a
Wrong,
prediction
wrong.
of the previous prediction.
Okay,
first
so
prediction,
we got it right
no,
9 times
so
out
the
of
status was 0.
16.
Then
So the
come on.
prediction accuracy then is 9 divided by
Here we come
16, which is 56.25%.
Here becomes 0. Here become 1, because plus 1. Here become minus 1, becomes 0 again. Branch not equal to 0, but it's 0. So we never branch again. So left, there's the previous. Next one, we never branch, so 0.
Okay.
Then the next one,
Same ah.
D become 1. Then you just go through, then it will be like, this time it will be taken already, right? Correct, right? Because this is 1.
What is the prediction?
Okay,
Prediction, okay,
Any
the first
questions?
2 prediction is from 4 lah.
Is it?
Yeah.
Action is what you gonna do ah.
Yeah. So not important. Most important is from now over there you got branch or not. So if there is 1, straight away you branch up. Because 1 is not equal to 0.
Yeah.
So
Branch to
taken.
all one.
So taken.
okay, so the next part of the
Straight away branch to
question
here. 1
says
minus 1.
to assume that we have
Then not
2
So not
bit
taken.
predictors
Not taken.
for branch
Feeling
B1 and
right,
B2
feeling
respectively.
Oh no.
So with a 2-bit
Right,
predictor,
that's right.
we have 4
So
states
far the whole
that
thing
the
I already know how
predictor
to
can
do
be
this.
in.
The whole thing
Okay, so and this shows the transitions between the different states. So for 0, 0, we predict not taken, and here we're
Answer.
fairly confident about the result. 0, 1, we also predict not taken, but we're not so sure. 1, 0, we predict taken, again we're not so sure. Well, 1, 1, we predict taken, and we're more confident. Okay, so if we're in 0, 0, and it's not taken, we stay in the same state. 0, 0 taken takes us to 0, 1. In 0, 1, if it's taken, it takes us to 1, 1. If it's not taken, it takes us back to 0, 0. 1, 0, if it's taken, takes us to 1, 1. If it's not taken, it takes us back to 0, 0.
lecture notes, right?
1, 1, if it's taken, we stay in 1, 1. If it's not taken, we go back to 1, 0. Okay, so we have the state transition diagram for that. So again, we could work out the table.
We don't actually, because no people do. I do lah, but like a bit wrong lah, don't want to say. 但我做这个，跟这个我 try，这个没有做。
我觉得这个最容易的
这个
一件事。
this is a value, then from the value you send inside to the instruction lah.
But the starting the question one, you need to go through see the
这个也是 okay.
easy
This is
I
not
don't
very
even know
difficult.
what is DADDI.
Yeah.
What is DADDI?
Okay, so again for this
Additional.
code,
Additional.
if d is equal to 0, neither branch is taken. If d is equal to 1, the first branch is taken, but the second branch is taken. And for other values of d, both branches are taken.
Yeah, I don't need to draw.
This one based on the transition right now.
Correct, it's based on tradition diagram. But the value state remain the same. But now is that the state
So
right we got.
here we start off
Different.
with the status of 0, 0 for
So
both
everything
b1 and b2.
different.
So b1 predicts is not taken, and it's correct, it's not taken, so the status remains 0, 1. And similarly for b2, it predicts not taken, the action is not taken, and stays 0, 0. For d has the value 1, we predict not taken, it is taken. So according to the finite state, according to the state transition diagram,
Taken.
we go to status 0, 1. For b2 is not taken, we predict not taken, the action is not taken, so we stay 0, 0. D has a value 2. We still predict not taken in state 0, 1, but in fact it is taken. So now we go to status 1, 1. Here we predict not taken, and it is taken. So we go from state 0, 0 to 0, 1.
Do we have the,
Here we get it right. We predict taken, it is taken, and it's staying in state 1, 1. Here we predict not taken, it is taken, so we go from 0, 1 to 1, 1. Here, predict taken, not taken, so we go back to 1, 0. And similarly here, predict taken, not taken, go back to 1, 0. Here, still predict taken, it is taken, so we change the status to 1, 1. And here, predict taken, but it's not taken, so we change the status to 0, 0. Okay, and here, we predict taken, it is taken, stay 1, 1, and so on. Here, we predict not taken, it is taken, so change to 0, 1. Predict not taken, it's not taken, so change to 0, 0. Okay, so what all you have to do is to look at the state transition diagram to work out the new status.
Here you predict taken because previously it's taken.
So here, what is the accuracy of our prediction? So again, we can count the number of times we got it right. So here we got it right 1 time, 2 times, 3 times, 4 times, 5 times.
Just now you look at just now you got 1 bit, so you only look at
6 times, 7 times.
Now 2 bit.
Here got it wrong, here got it
So
wrong,
you need to
here
look at the past.
sorry, count again. Got it right 1 time, 2, 3, 4, 5, 6, 7, 8. So we got it right
1 bit easier.
8 times out of 16. So in this case, the prediction accuracy is 8 divided by 16, or 50%. So for this particular example, in fact, the 2-bit predictor doesn't perform as well as the 1-bit predictor.
Where you get that value?
But
Where you
that
get
is
that
just
value?
for this one particular
again,
example,
8 divided
which
by
is
16.
rather sort
because
of
it's
unusual
total you got
code.
16 prediction, but only 8 you get it correct. So 8 divided by 16 only means that this table, right, there's only 50% that accuracy that you will get it
1,
correct.
2, 3,
And 0 and
Okay, so are there any questions
0,
on that?
0, then 1, 1, 1, 1, 1 is 1, 2, 3, 4, 5, then 6,
So if there's no questions, we'll stop there.
5, 6, 7, 8, 9.
For next week, which is e-learning week,
I don't know.
again, we're planning to make a recorded tutorial available for you. Okay, so there'll be a recorded tutorial for tutorial 5 on adventure. And we'll also arrange a question and answer session. So you can look at the recorded
Ask him,
tutorial first,
Ask him
and
to
then
come
if
for
you
us,
still
ah.
have some questions about
16 I know is
the
16.
Yeah, 16 is them not
8, just now 8, I hear from him say about P1 is that the value is 0.
Okay, so we'll stop there. Thank you.
Value is 2, 3, 1, 2, 1. Eh? No.
1.
Why is it 8?
3, 4, 5, 6, 7.
I don't understand.
Then
一点点啊，一点点。
correct.
How the
Actually,
prediction
the
is how did they
prediction
get
is correct lah.
prediction? Yeah.
Prediction actually
Prediction
the
is
same ah.
the first prediction is you take as because you are stating at the start, so you predict this value 0 right, will not be taken. So the action right, whether you
So at the start you always be not taken.
Different. 2.
true,
Different. 3, 4,
true.
5.
Then after that when you
Then
reach
the action is
Seven.
why the action is not taken.
because you go and calculate value 0 right, then you sign inside
The
in
16
this
is
equation
taken,
you see
the
whether
taken, not taken.
see whether the action is taken. If the action is not taken right, then your P1 action will not be taken. Then your current state right will still remain at the current state.
Out the 16.
Then you go to your value 1, then you do the same thing again. So your prediction of the previous thing is that it's not taken.
So the first
Not the not taken meh?
so the first and second prediction is depend on the first one, is it?
Yes. Correct.
Wah, if
Depend on
that's
the
not,
first
they're
position or
not
the first
16,
action.
just like that.